Welcome to the video lecture on limits ad infinity. In this lecture, we're going to talk about the limit of a function as x goes to positive or negative infinity. So let's start by looking at the function 3x squared over x squared plus 1. Here I have a table of values, and we're going to look at x values that get larger and larger in the positive direction and in the negative direction, and we're going to see what happens to those function values, those y values. So in this direction, we're letting x go to positive infinity, and these x values are getting bigger and bigger and bigger. And in this direction, we're letting x go towards minus infinity, so these x values are getting more and more negative. So let's see what the y values do correspondingly. So as we go to positive infinity, these y values are getting closer and closer to 3 from below, from slightly less than 3. And then in the other direction, same thing. These y values are getting closer and closer to 3 from below as well. So let's put this together into a graph. We know that we have a function that goes through 0, 0, and it goes through 1, 1.5 on both sides, and then 10, approximately 3. So we're getting closer and closer to 3 as we get this way. So our graph is going to look something like this. And likewise on the other side as well. This graph is symmetrical. So here's the graph of our function. And what we see is that as x increases without bound, which means as x gets larger and larger and larger, these y values are approaching 3, and as x decreases without bound towards minus infinity, the y values are also approaching 3. So these are called limits at infinity, and the notation would just be the limit as x goes to infinity of our function is 3, and the limit as x goes to minus infinity of our function is also 3. And the importance of limits at infinity is the fact that graphically what you'll see is a horizontal asymptote. So if these limits at infinity actually exist and equal a finite number, then you're going to have a horizontal asymptote showing up on your graph. And because it's horizontal and the equation of a horizontal line is always y equals a constant, this would be the equation y equals to 3. So limits at infinity lead to horizontal asymptotes. So here's our formal definition. We say that the line y equals to L is a horizontal asymptote of the graph f if the limit as x goes to minus infinity of our function is L, or if the limit as x goes to positive infinity of our function is L. And you want to note that the graph of a function of x can have at most 2 horizontal asymptotes. These two L's don't necessarily have to be the same thing going to the right and to the left. So as I go to positive infinity, I might have one asymptote, and as I go to minus infinity, it is possible to get a different asymptote. Now we have talked about some important limits already, and I just want to review a couple of the key properties that we should already know. So suppose that we have the limit as x going to 0 through the positives of the function 1 over x. So in other words, we're taking 1 over something that's getting smaller and smaller and smaller, then 1 over that gets bigger and bigger and bigger. So this limit goes to infinity, and since 0 was going through positives, this is going to go to positive infinity. Likewise, if I have 1 over 0 but through the negatives, then this would still blow up, but it's going to blow up in the negative direction. So this would go to minus infinity. So 1 over something small gets big. In the reverse direction, 1 over something big is going to get small. So as x goes to infinity, 1 over that is going to go to 0, or if x goes to minus infinity, that's also going to go to 0. And you can see that just from the graph of 1 over x, which is our nice reciprocal function. So as x gets bigger this way, our graph is getting closer to 0, and as x gets bigger this way, our graph is getting closer to 0. So 1 over something small gets big, 1 over something big gets small. Now what if you don't just have a 1 on the top? What if you have a constant c? That's okay. What if you have, instead of just an x in the bottom, a power of x, like an x squared, x cubed, or whatever, with a coefficient in front? That's okay too. In general, we can say that the limit going to either positive or negative infinity of a constant divided by a constant times a power of x is still going to go to 0, because your numerator will be fixed at a specific constant and your denominator is getting bigger and bigger and bigger, so the reciprocal gets smaller and smaller and smaller and goes to 0. So we're going to use that generalization to find a lot of these limits at infinity. So for example, if I want the limit as x goes to infinity of 3x minus 1 over 2x minus 5, what I'm going to do to try and use this generalization up here is I'm going to take this function and I'm going to look at what the highest power of x is that I see. Now in the top I have a 3x minus 1, so that's dominated by that x to the first term. That's the highest power of x term that I have in the numerator. Likewise, in the denominator, it's dominated by that 2x term because that's your highest power of x. So what we're going to do is we're going to multiply this by a fancy version of 1 so that we're not changing our function at all. But what I'm going to do is I'm going to multiply by 1 over whatever that highest power of x was, which in this case is just x to the first. So I'm going to multiply by a 1 over x on the top and on the bottom. So we're really just multiplying by a 1, so this should still give us an equivalent limit. Now let's go ahead and distribute that 1 over x across. 3x times 1 over x is just 3. The x's cancel. And negative 1 times 1 over x is minus 1 over x. On the bottom, 2x times 1 over x is just 2. And negative 5 times 1 over x is negative 5 over x. Now, the limit of a quotient is the quotient of the limits. The limit of a difference is the difference of the limits. So what I'm going to do next is take the limit of each of these 4 pieces. So the limit of 3 is going to stay 3. The limit of a constant is that constant right back again. Now, what would be the limit of 1 over x? Well, we said up here that that was 0. So this numerator is going to go to 3 minus 0. In the bottom, the limit of 2 stays 2, and the limit of 5 over x also goes to 0 because of our generalization. It doesn't matter that we don't have a 1 on top. Any constant is okay as long as you have that power of x in the denominator. So these both go to 0, and what we're left with is 3 minus 0 over 2 minus 0, or 3 halves. Now the shortcut to this is to notice that what dominates in our numerator and our denominator is going to be the term that's the most important term as x gets really, really big. And that should make sense, because if you're taking 3x minus 1 and plugging in a very, very large number, then obviously 3 times that really large number is going to be much bigger than minus 1. So this 3x is what dominates. On the bottom, the same thing is true. The 2x will dominate. And if you look at 3x divided by 2x, those x's are canceling out, which is where we're getting that 3 halves from. So it's the dominant term divided by the dominant term that's going to make a difference in our final limit. Okay, let's try a few more here. If we take a look at this next one, I'm going to be careful on this next one and show you all the necessary work, and then we'll see the shortcut or the generalization here. So doing the same thing that I did on the last example, I'm going to look at my powers of x in the numerator and in the denominator, and I'm going to multiply by 1 over whatever that highest power of x is. So I have an x squared as my leading term on top and an x squared as my leading term on bottom. So my highest power of x in all of this is an x squared. So let's multiply by 1 over x squared. So that's going to give me, in the numerator, when I distribute, 2x squared times 1 over x squared is a 2, minus, when I multiply 5x times 1 over x squared, one of those x's will cancel, but one will still be left in the denominator. So I'll have that 5 on top and that x in the bottom. And then 7 times 1 over x squared is 7 over x squared. In the denominator, 7x squared times 1 over x squared is 7. Negative x times 1 over x squared is a negative 1 over x because one of the x's cancels. And 4 times 1 over x squared is 4 over x squared. Now by our generalization, a constant over a power of x goes to 0 as x gets really big. So this is going to go to 0, this is going to go to 0, this is going to go to 0, and this is going to go to 0. So the only thing that's left is this 2/7, so that means 2/7 is my answer. Okay? The shortcut would be to notice that what dominates here on top is that 2x squared, and what dominates is that 7x squared on the bottom. The x squareds would cancel, and we're just getting that ratio of those two coefficients for our final limit. Now if we look at the next example, this time we have an x cubed on top and an x squared on the bottom. So what we're going to do is we're going to multiply this by the highest power, 1 over the highest power of x, which is this time an x cubed. So I'm going to multiply by 1 over x cubed on the top and the bottom. So when I do that in the numerator, the 2x cubed and the 1 over x cubed cancel to give me just the 2. 5x times 1 over x cubed gives me minus 5 over x squared, and then I'll get a 7 over x cubed. In the bottom, 7x squared times 1 over x cubed leaves me with the 7, but I still have an x in the bottom. A negative x times a 1 over x cubed is a negative 1 over x squared, and 4 times 1 over x cubed is 4 over x cubed. So using my generalization, any term that has a constant over a power of x is going to go to 0 as x goes to infinity. So 5 over something really, really big is going to get really, really small. So this goes to 0, this goes to 0, this goes to 0, this goes to 0, and this goes to 0. So what we're left with is that 2 on top and something that's going to 0 on the bottom. Now what's that going to do in terms of a limit? What happens to 2 over something really, really small? Well, that's going to blow up. So this is going to be infinite or d and e. Okay? So if the degree in the numerator is bigger than the degree in the bottom, then your limit will be d and e. Now let's look at what happens if the degree in the denominator is bigger than the degree in the numerator. So this time, my highest power of x out of all of these terms is that x to the 6th. So we're going to multiply by 1 over x to the 6th on the top and the bottom. So 2x cubed times 1 over x to the 6th is 2 over x cubed. Minus 5x times x to the 6th is minus 5 over x to the 5th, and then I'll get a plus 7 over x to the 6th. On the bottom, when I multiply 7x to the 6th over x to the 6th, I just get 7. Negative x times 1 over x to the 6th is negative 1 over x to the 5th. 4 times over 1 over x to the 6th is 4 over x to the 6th. So a constant over a power of x goes to 0 as x goes to infinity. So this will go to 0, 0, 0, 0, and 0. And that means what we're left with on top is just zeros, and on the bottom we're left with 7. And 0 divided by 7 is just 0. So to summarize, oops, sorry about that, if we have the coefficient, the degrees on the top and the bottom are the same, then our limit will just be the ratio of those coefficients. If the degree on top is bigger than the degree on the bottom, then our limit will be d and e. And if the degree on the bottom is bigger than the degree on the top, then our limit will be 0. So that's what this summary says down here. If the degree of the numerator is less than the degree of the denominator, the limit will be 0. If the degree of the numerator is equal to the degree of the denominator, the limit is the ratio of those leading coefficients. And if the degree of the numerator is greater than the degree of the denominator, then the limit does not exist. Horizontal asymptotes occur when the degree of the numerator is less than or equal to the degree of the denominator. In other words, whenever that limit is either a constant, like our ratio 2/7 here, or 0. If you get a limit that's D&E, then that means you do not have a horizontal asymptote. So if the limit is D&E, then there will be no horizontal asymptote. If the degree of the numerator is exactly 1 more than the degree of the denominator, that's when we get what we call slant or oblique asymptotes. So instead of being horizontal, they'll be at an angle. So let's practice finding some of these asymptotes. Now when it says find the asymptotes of this function, that includes all types, so vertical and horizontal asymptotes. So if we look at this function right here, let's start with our vertical asymptotes. And in order to find vertical asymptotes, you need to figure out where that denominator could potentially become 0. And to do this, since it's quadratic, it would be best to totally factor everything, all the numerators and all the denominators. So if I factor the numerator, I have a difference of squares, x plus 1, x minus 1. And the denominator, when I factor it, I'm going to need an x and an x. And 2 times 3 would give me 6. I want the 3 to be negative and the 2 to be plus, so that I get a minus 1 in the middle. Now the reason I factored the numerator as well is because vertical asymptotes don't just occur where the denominator is 0. They occur where the denominator is 0 as long as the numerator is also not 0 at that same place. Because if one of these factors on top and bottom matched, then that wouldn't cause us to have a vertical asymptote. It would cause us to have a hole in our graph. So you need to look at where the denominator equals to 0 as long as the numerator does not equal to 0 there. So because we don't have any common factors on the top and the bottom, so nothing would cancel out, we don't have any holes, which means the places where this denominator is equal to 0 are going to be vertical asymptotes. X plus 2 equals 0 at negative 2, and x minus 3 equals 0 at x equals positive 3. So those are my 2 vertical asymptotes. Now let's find our horizontal asymptotes. So to find those, that's taking a limit as I go to infinity. So this would be the limit as x goes to plus or minus infinity of this function. Now for rational functions like this, where it's a polynomial over a polynomial, your limit going to positive or negative infinity will be the same. That's always true. So if you have a rational function, you won't need to bother with checking to the right and to the left, going to plus or minus infinity. They'll give you the same result. And our shortcut was to look at those dominant terms. So here, the degree of the top is the same as the degree of the bottom, so this is dominated by x squared over x squared, and those would cancel out to just a 1. So the ratio of those coefficients is just a 1, which means we do have a limit, which means we do have a horizontal asymptote, and it would have as its equation y equals 1. So these are my 3 asymptotes. Okay, let's try that again for this rational function over here. Again, it's a polynomial over a polynomial. So let's start with our vertical asymptotes. Before I figure those out, let's factor the denominator completely. I need a 5 and a 3 to get 15. I want the 5 to be plus and the 3 to be minus. Since none of my factors on the top or the bottom are the same, I don't have any holes. So that means my 2 factors in the bottom are going to give me vertical asymptotes. So I will have one at x equals negative 5 and x equals positive 3. Then to find my horizontal asymptotes, we're going to take the limit as x goes to plus or minus infinity. It'll give me the same answer whichever way I do it of this rational function. and I'm going to look at what dominates in the top over what dominates in the bottom. I have an x over an x squared. So that is going to reduce into a 1 over an x, and as x goes to infinity, either plus or minus infinity, this is going to go to 0. So this is the case where the denominator has a bigger degree than the numerator, so the limit is 0, which means my horizontal asymptote does exist, and it has as its equation y equals to 0. So these would be my 3 asymptotes. Now let's look at some horizontal asymptotes of functions that are not necessarily rational. So these could potentially have 2 or more different horizontal asymptotes, 2 asymptotes or 1 asymptote or no asymptotes. We just have to look and see what happens in that limit. So this is called a logistic function, and it's 1 over 1 plus e to the negative x. So to find the horizontal asymptotes of this logistic function, that requires that I find these limits at infinity. And because this is not just a straightforward rational function, I am going to have to look at my 2 separate limits individually, the limit to positive infinity and the limit to minus infinity. When it's not a rational function, these could potentially give me 2 different answers and therefore 2 different asymptotes. Now to figure these out, it's going to be helpful to know what the graph of e to the negative x does. So hopefully you all know that e to the positive x, e to the x, is just an exponential growth graph like this. Okay, as x gets really, really big, the graph grows bigger and bigger and bigger. So this would be e to the x. E to the negative x is the horizontal reflection of that because we have a negative up there near that x. So we just flip this graph over the y-axis to get the graph of e to the negative x. Now let's take a look at that graph and figure out a couple of limits here for a moment. Based on this black graph, what would be the limit as x goes to positive infinity of this function? So if I'm going to positive infinity, that means I'm going this way. So what's happening to my graph as I go to the right? Well, this black graph is going towards 0. So this limit goes to 0. Now let's look in the other direction. What happens to this black graph as I go to minus infinity? So now I'm going in this direction, but we're looking at the black graph. So as the x's go this way, the y's are going up, 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 up. So that means the limit is going to positive infinity. So we're going to use those 2 pieces of information to find these limits over here. So when I have this quotient, remember the limit of a quotient is the quotient of the limits. The limit of a sum is the sum of the limits. So to find this limit, I'm just going to take the limit of each of these 3 pieces. And the limit of 1 on top is going to just stay 1. The limit of 1 on the bottom is going to stay 1 because the limit of a constant is a constant. And then here is where we're going to use these limits we had over here. The limit as x goes to positive infinity of e to the negative x, we said that was 0. So this is going to go to 0. So that means this is going to reduce and have an actual value of 1. So that means we have 1 horizontal asymptote with an equation y equals to 1. Now let's do this one. The limit of the top goes to 1, the limit of the 1 in the bottom goes to 1, and the limit as I go to minus infinity of e to the negative x goes to positive infinity. Now think about what that's going to go to. 1 plus infinity is still infinite. So this is acting like 1 over something really, really big. Well, what happens to something that's 1 over really, really big? It gets really, really small. So this is going to go to 0. And that means we also have a horizontal asymptote in the other direction that's equal to 0. So this would be an example of a function with 2 separate horizontal asymptotes, one going to the right and one going to the left. Another common example that might have more than one horizontal asymptote is a limit of a function with a radical in it. So let's take a look at this next example. The limit as x goes to minus infinity of negative 3x over the square root of x squared plus x. So in this problem, we have to be a little bit careful. It's tempting to use our shortcut and look at what dominates on top and bottom, just like we would normally do with our rational functions. And in fact, we are going to do that, but we have to be a little bit careful how we handle the denominator because of that square root. So obviously on the top, what dominates is just that negative 3x term, because that's the only term we have. On the bottom, what dominates is that x squared, but it's in a square root. So you have to think about how does that reduce. And sometimes we get a little bit lazy with this, and we say, oh, well, the square root of x squared is just x, because the square root and the square cancel each other out. And essentially that is true, but it's not really technically just x that we get. It's really the absolute value of x, because a square root, the way this is defined, we want the positive answer. And so you need to force your value to have a positive answer. And how is the absolute value of x really defined? Well, we could treat it as a piecewise function. You get back just normal old x if x is already positive to begin with. But if x is negative, then you need to give back the opposite of x. So in other words, if x was negative 3, then my answer should be the opposite of negative 3, which is positive 3. So this is the formal way that we define the absolute value of x. Now, why am I bothering to do all this? Because we have to look at which direction we're looking at. As x goes to minus infinity, what kind of x values are those? Those are negative x's, these right here. And so when I go to simplify square root of x squared, what should I be getting back for an answer? Not just plain old x, but actually the opposite of x, because we're dealing with negative x values, and we want to make sure that we're getting a positive answer back, because this was a positive square root. So just be really careful with these square root problems. Look at which kinds of x's you're looking at. If you're looking at positive x's to positive infinity, then this would have just simplified to plain old x. But if you're looking at negative x's going to negative infinity, then you need the opposite of x as your reduced answer. So now we know what dominates on the top and what dominates on the bottom. These x's are going to cancel out. Those negatives are going to cancel out. And that means this limit is going to equal to 3. And so that means our limit going to minus infinity of this function is equal to positive 3. Now if I did this same exact problem, but I went to positive infinity, then I wouldn't have had that extra negative in the denominator, and this limit would equal to negative 3. So I would have had a different horizontal asymptote going to the right than I do going to the left. Now we're going to finish off by looking at limits at infinity involving some trig functions. So let's take a look at the limit as x goes to infinity of cosine of x. Now think about the graph of cosine of x here for a moment. Hopefully you remember what that looks like. It's this U-shaped graph that just repeats itself, going on and on and on. It's periodic. So if I'm going to infinity in this direction, what's happening to this graph? Is it getting closer and closer to a certain value? No. This is a limit that is dne because it oscillates infinitely often between -1 and 1. Goes back and forth, back and forth, and back and forth. It doesn't get closer and closer to a single limit value. So the limit of cosine of x is dne as x goes to infinity. Now let's look at the limit as x goes to infinity of sine x over x. Now this should look slightly familiar to you. In a previous lecture we have talked about the limit of sine x over x. However, in a previous lecture we weren't going to infinity, we were going to 0. So we have done before in the past the limit as x goes to 0 of sine x over x, and you need to have memorized that that goes to 1. And the reciprocal of this is also true, since the reciprocal of 1 is still 1. Okay, so unfortunately this isn't quite the same thing, so we have to be a little bit more creative in how we figure this out. Now initially you could think about trying to plug in infinity, and sine of infinity has the same issue that cosine does. It oscillates back and forth. So you might think that that doesn't have a limit. And then x going to infinity in the bottom has issues as well. So we have a little bit of a problem just trying to plug in infinity. So we're going to be a little bit more creative to figure this out. And I'm actually going to use the squeeze theorem to prove what this limit is. Now the way I'm going to do that is I'm going to use the fact that I know that the sine function is bounded between -1 and +1. It's always in between those two values. That's true. So now what I'm going to do is I'm going to take this triple inequality here and I'm going to divide everything by x. So I'm going to divide the left side by x, the middle by x, and the right side by x. So that will still be true, that inequality will still be true. And so by the squeeze theorem, what we can now do is take the limit of each of these three pieces. So the limit as x goes to infinity of -1 over x should be less than or equal to the limit as x goes to infinity of sine x over x is less than or equal to the limit as x goes to infinity of 1 over x. And what do we know about the limit of 1 over x as x goes to infinity? Well, that's going to be 1 over something big, which means it goes to 0, it gets small. And -1 over something big also gets small and goes to 0. So each of these two ends goes to 0, which forces the middle function, or the middle limit, to also have to go to 0 as well. So we've just proven that this limit, as x goes to infinity, of sine x over x is defined to be 0. Okay, so let's summarize at the top of the next page some of these important limits that we need to know. So we just showed that the limit as x goes to infinity of sine x over x goes to 0. Now think about what the reciprocal of that would be. If I flip over x over sine of x, what would that turn out to be? Well, it should be the reciprocal of whatever this limit was over here. And what's the reciprocal of 0? Well, that would become 1 over 0, which is undefined. So this reciprocal limit turns out to be d and e. And then these two limits down here are the ones we've done in a previous lecture. The limit as x goes to 0 of sine of x over x we found was 1, and the reciprocal of 1 stays 1. So that also has a limit as well. Okay, let's try some of these now. So on this next example here, we want the limit as t goes to infinity of t over sine 4t. Now, first thing I want you to recognize is this 4 next to our t is not a constant that I'm allowed to pull out. So in other words, sine of 4t is not the same thing as 4 times sine of t. This 4t is part of our angle, part of our argument of sine, and it is stuck inside of that sine function. So you're not allowed to pull out your constants that are inside of your trig functions. So the only way to handle this is to manipulate this a little bit. And if you remember again from a previous lecture, I've talked about in the past sine of box over box as box goes to 0. Well, that same idea applies for these infinite limits as well. So what we're going to use is the limit of sine of box over box as that box goes to infinity will still be 0. So it's just a generalization of this limit theorem, where instead of just having a plain old x, I can have any expression that I want. And in this problem, I have a 4t instead of an x. And it would also be true in the reciprocal form as well. So if I have the limit as box goes to infinity of box over sine of box, as long as these match on the top and the bottom exactly, and that expression is still going to infinity, then this limit will be d and e. So that's what I'm going to use here. Now, in order to make these match, right now what's in my box is this 4t, and on top I only have a t. So what I'm going to do is I'm going to put a 4 in front of that t so that these boxes match, but then I'm going to counterbalance that 4 by putting a 4 on the bottom as well. So I've really just multiplied by a fancy version of 1. I multiplied by 4 over 4 on the top and the bottom, and I grouped these two together, and I put this 4 out front. So what we end up with is the limit as t goes to infinity of 4t over sine of 4t. This 4 is a function, is a constant. It's in the denominator, so you can think of it as a 1/4, and because a constant times a function, it allows you to pull that constant outside of your limit. I'm allowed by my limit properties to pull out that 1/4. So the limit of 1/4 times my function is 1/4 times my limit. We're allowed to pull those constants out. So this is now what I'm left with. And using my generalization up here, since these now match exactly, this limit is going to potentially go to d and e. There's one last thing that I want to check though. Because we changed this box to a 4t, let's make sure that it's still going to infinity. So for example, if t is going to infinity, does 4t still go to infinity? Sure, because if t gets really, really big, then 4 times t will certainly be really, really big. So even though I have a t down here, that still implies that 4t, or whatever was in my box, is also going to infinity. So I am allowed to use this sort of limit theorem up here. Since this limit is d and e, multiplying that by 1/4 is still going to be d and e. So my final answer is d and e. Okay, let's try another example. Here we want the limit as x goes to infinity of 5/2 plus the ln of x squared plus 1 over x squared. So we're going to use our limit properties here. The limit of a sum is the sum of the limits. So I'm going to break this up into the limit of the 5/2 plus the limit of this ln function. The limit of a constant is that constant right back again, so the limit of 5/2 will stay 5/2. And then over here what we can do is swap the limit and the ln. So in other words, I'm going to figure out what the limit of this input function is, this rational function x squared plus 1 over x squared is, figure out what that is, and then take the ln of that answer. Well, what is the limit of x squared plus 1 over x squared? If x is getting really, really big, then that's going to be determined by what dominates on the top over what dominates on the bottom, and those are equal powers, so they're going to cancel out, and the coefficients in front reduce to a 1. So this limit is just going to be 1. And now we want to take the ln of that answer. Well, what's the ln of 1? E raised to what power gives you 1 back again? 0. So ln of 1 is 5/2, which means this limit is going to be 5/2. Okay, couple more examples. The limit as x goes to infinity of 3x squared minus 6x all over x plus 1. This should be an easy one because it's just one of our nice rational functions. So to determine this limit, you just look at what dominates on the top over what dominates on the bottom. And since the degree on the top is bigger, then this is going to reduce to a 3x. And in the limit, that's going to stay infinite. That's going to go to infinity. So we would say that this is a limit that is d and e, does not exist because the degree on top was bigger than the degree on the bottom. Okay, in our last example, we want the limit as x goes to infinity of x times tangent 1 over x. Now, because this limit has a tangent in it, and none of the limits that we've mentioned previously today involve tangents, they all involve sine functions, we're probably going to want to change that tangent so that it's rewritten in terms of sine. So that's the first thing that I would suggest doing on a problem like this. And I'll warn you in advance here that this problem is a tricky one, and you probably wouldn't think to do all the little steps that we're going to do here without some practice and some experience. So I'm going to show you how to do this one so that eventually when you are given a similar problem, you can use the same tricks and make your limit work. So what I'm going to do is I'm going to change this tangent into sine of 1 over x divided by cosine of 1 over x. So just getting rid of that tangent function. Now at this point, what I'm going to do is I'm going to rearrange my terms slightly. So what I'm going to do is I'm going to take this cosine of 1 over x, which is in the denominator, so I want to leave it in the denominator, and I'm just going to stick it underneath a 1. Now the other two pieces that I have are that sine of 1 over x, which is in the numerator, so that's going to stay there, and then we have this x, which initially is in the numerator as well. But here's one of my first tricks that I'm going to pull. I'm going to rewrite that x as 1 over 1 over x. And hopefully you agree that that is a true statement, since 1 divided by 1 over x is the same as 1 multiplied by the reciprocal x over 1. So 1 divided by 1 over x is the same as 1 times x over 1, which is just x. So we're just rewriting it in a very fancy way. So this x is going to come down into the bottom down here and turn into a 1 over x in my denominator. So that's my first trick. Now why would I possibly want to do that? The reason why is because this sine function is not sine of x, it's sine of a box, right? It's sine of some different kind of stuff. And in order to use some of those limit properties that we have up above, I need to have that same box in the denominator. And by manipulating this x and turning it upside down, now I've forced these two boxes to match, which is good news for us. Now because this box is complicated, it's a 1 over x, what I'm going to suggest doing next is my second trick, and that's going to be a change of variables. So let's define a new variable y to be 1 over x. So that's going to turn this problem into 1 over cosine of, and here's that 1 over x, so that's going to turn into a y. And then this is going to become sine of y over y. So I'm trying to simplify the problem so that it looks much cleaner than what I started with. Now there's one issue. Because we're changing our variable to y, we need to figure out what's going to happen down here in our limit. We know that x is going to infinity. So what does that force 1 over x, which is what we're calling y, to do? Well, if x is getting really, really big, then 1 over something big is going to get small. So if x is going to infinity, that's the same as saying that y, the reciprocal, is going to 0. So I've just changed up my variables to make this much cleaner looking. Next thing I'm going to do is the limit of a product is the product of a limit. So I'm going to separate these two different fractions into two different limits. So I'm going to take the limit as y goes to 0 of 1 over cosine y times the limit as y goes to 0 of sine of y over y. And now let's do this first one right here. As y goes to 0, this becomes 1 over cosine 0. And cosine of 0 is 1. So 1 over 1 just goes to 1. Now I need to figure out what to multiply that by. So now I go to this limit over here, the limit as y goes to 0 of sine of y over y. Let's look in our list up above here. That's this one right here. Instead of using x's, I'm using y's. So the limit, as y goes to 0, of sine of y over y, so same exact formula as this, but with a change of variable, that's still going to be 1. So this limit down here goes to 1 as well. So the product equals to 1. So our final answer is that this limit is 1. So this last example here had a lot of manipulations involved, changing tangent into sine over cosine, changing this x into 1 over its reciprocal, changing 1 over x into a new variable y, and changing what this limit approaches so that it's in terms of that new variable y. So there's a lot of things going on in that last example. Okay? With practice and experience, you'll get the hang of these. All right, that concludes our lecture on limits at infinity. Good luck.